Okay, so everybody good with resting membrane potential and action potentials and graded potentials, all those potentials we talked about yesterday. So we can start now applying this to how muscle tissue and nerves eventually work. And so we're focusing on cardiac muscle. We can start talking about kind of how the two different types of cells that make up the wall of the heart actually perform. So remember, there are two kind of types of cardiomyocytes. There are contractile cardiomyocytes, and then these things we call pacemaker cells, or funny current cells, or autorhythmic cells. You see lots of names for them. And we'll talk about that. Their major differences are really going to be what proteins are found in their membranes, which allows them to behave slightly different from one another. So one of the most interesting things about cardiac cells, particularly the contractile cells, which you remember are built kind of similarly, at least internally, on how actin and myosin is organized, right? They're striated muscle. One of the major differences is what the action potential looks like. So up top here, this is what a typical action potential and contraction phase of muscle cell that is in the arm or the leg, what we call skeletal muscle. And what you'll see here is in blue, the action potential is really short. All right, it's really fast. It's a couple milliseconds. For contraction to happen, when you move biceps, for contraction to happen, you're hitting that muscle about 80 or 90 times a second with action potentials. Okay? That's because the action potential is so fast that it takes, if you just use one action potential, the muscle doesn't even contract until after the action potential is over with. And it takes that much time in order to see contraction. And then the contraction is going to be kind of curved like this, a nice little hump, right? As far as increase in force, a peak of force, and then a drop of force, right, as the muscle relaxes. Look at cardiac muscle. The action potential and the contraction phase here, the force phase, overlap each other a lot more. What I want you to notice here with the action potential is it starts off looking really similar to this, right, as far as how contraction starts, but then instead of dropping immediately, it comes down a little bit and then plateaus for a long period of time, and then finally repolarizes, okay? So we'll talk about why when we get to the contractile cells. So these cardiac muscle cells that contract have very long action potentials, and it's really because of the type of calcium channel they have. All right, this long plateau phase is maintained by a specialized calcium channel that's called an L-type channel, right? L-type meaning long-lasting. That's what the L stands for. And that's why you have this plateau stage. There's no L-type calcium channel up here in the skeletal muscle, right? They're going to rely mostly on sodium and not calcium to run or to provide the reversal in membrane potential. Skeletal muscle can do a physiologic feat called tetanus when the muscle does this. That's what biceps is doing, right? When it's contracting. Do you want the heart to do this? No, that's called heart attack. Okay, you want the heart to contract, relax. Contract, relax. Squeeze blood, fill. Squeeze blood, fill, right? You don't want it to do tetanus. And that's what tetanus is sustained contraction, right? With no relaxation between the contraction phases, okay? Tetanus, it can occur in skeletal muscle because of the really short action potentials. You can send one right after, one after another, and that'll keep the muscle in the contraction phase. And that is what tetanus is. And that's how your muscles behave. Your skeletal muscles behave in real life. They actually are performing tetanus when they contract. It's a nice, smooth, sustained contraction. Cardiac muscle doesn't have the ability to do that because of this plateau phase, and the muscle can't recycle and reset, right, as fast as skeletal muscle can. So the advantage of prolonged contraction in prevention of summation of the action potentials, that is adding action potentials up, is you can't do tetanus. And therefore, you're going to contract completely and relax before you can contract again, which allows your chambers to fill effectively, right? So that you're actually moving blood very effectively by allowing for this entire contractile cycle to occur before you can actually contract again. The other advantage of this is it helps provide the basic rhythm of the heart. So you shock the heart, then it contracts, and then you can shock it again, and it contracts, and you shock it again, and it can contract. And there's a rhythm to that. Right? You're going to shock the heart about 70 to 90 times a minute, and that means you're going to have 70 to 90 beats per minute, right? Which we call heart rate, correct? When you measure heart rate. So we'll come back to the contractile cells and talk about how this action potential plays out and all the channels involved. But there's another set of cells that are called autorhythmic cells, and their action potential looks nothing like this. And that's because their job is to provide the autorhythmicity or the spontaneous depolarization of the heart. And these are called funny current cells, all right? And they produce an action potential that's going to look more like this. So go back, we've got a spike, plateau, relaxation, right? Spike, plateau, relaxation. Spike, plateau, relaxation. Right? That's how the contractile cells depolarize. Here, it's depolarization and then repolarization. Okay, repolarization simply means you reverse the depolarization, right? So if it goes to positive 30, you bring it back to rest. So notice it's not quite as dramatic as the skeletal muscle, which is up and down. It rolls a little, so it's up, a little plateau, and then down. But the one thing I want you to notice is here's rest, right? 60 millivolts. Here's rest, but notice it doesn't stay at resting membrane potential. It immediately creeps. Do you see that? When it hits 60, it doesn't stay at 60. It starts positive again. Then it's going to hit threshold at negative 40 and do a contraction, an action potential again. And then it is going to repolarize and starts creeping again. Action potential. Creep, action potential, creep. This creeping always happens. It's always becoming positive once it hits resting membrane potential. And the reason for this creep here, this is the weird current, because it's not being maintained at rest, this is called funny current. And there are specialized protein channels that are responsible for this. And for a long time, the only place we could find these channels were in pacemaker cells. It's the only place that's where they were first discovered. It's the only place we knew where they were. But recently, they've been found also in the nervous system. Right? So they help with some of the cyclic action potentials produced in our central nervous system. Now, the first reason for this creeping is either because of fewer leakage channels, right? Potassium leakage channels are the important ones here. Or you'll go out, if you do some research, it's because some of these potassium channels can close, right? And what closes them is when they hit negative 60 millivolts, okay? When they hit negative 60 millivolts, a couple of the potassium leakage channels close, which is going to allow for a little more positive charge to build up, right? Now, I will tell you, not enough of them close to reach threshold by themselves, but it starts the creeping, right? It starts this creeping process. Then we're going to have to rely on two other channels here in order to kind of get us to reach threshold. So the heart is myogenic and spontaneously myogenic because it can produce action potentials spontaneously, which is going to cause contraction, myogenesis, muscle genesis, or contraction. These are called pacemaker potentials or funny current potentials that arise here between the negative 60 and when we reach threshold. And notice there's a slope to this, right? There's a basic slope. what I would call normal slope, right? Which is going to control normal heart rate, which is going to be about 60 to 80 beats per minute on average, right? Now, you can use the nervous system to do this, to make the slope go up or to make the slope go down, right? Steepen it, if you will, or to kind of flatten it out. You can imagine if I steepen it, you're going to speed up heart rate, right? If I flatten it, you're going to slow heart rate, right? So what the nervous system can do is change the slope, if you will, of this funny current and either slow or speed up heart rate. But the interesting thing is you don't need the nervous system to control basic heart rate. The heart controls itself, right? What the nervous system does is tweak. It comes in and tweaks things, right? So if your heart rate's too high, then your nervous system can come in and slow it down. If your heart rate's too slow, your nervous system can come in and speed it up, right? So for example, when you're sitting here resting and you're getting really comfortable because you're listening to me and I'm boring the hell out of you, right? Your heart rate is normal heart rate. Now, when class is over and you start thinking, oh God, what do I got to do next? And you get up, that's when the nervous system shocks your heart a little bit and gets your heart beating, right? Helps you get moving. Or somebody comes up and grabs you and your heart rate increases, right? Those types of things are when the nervous system kind of can interject, right? Come in and interject. But the heart itself can kind of control its own rhythm. And a lot of that's genetically controlled, right? Because some of us have really low heart rates. Some of us have really high heart rates. And some of that has to do with genetics. Some of it has to do with stress, right? Those types of things. So you can chemically and neurally control the heart. And what's the difference between them? When I say chemically, we're talking about hormones, right? Epinephrine's a great example of this, the flight or fight response. Somebody grabs you or scares you, jumps out of the closet, like my kids like to do, right? Scare the hell out of my wife. No. You release a burst of epinephrine, right? And that can speed up heart rate. Or you have nerves that actually travel to the heart that can speed up or slow down heart rate. So the two parts of the nervous system that are responsible for this are what are called the autonomic nervous system. There's two branches or two categories of autonomic nerves. They're called parasympathetic nerves and sympathetic nerves. And so these are part of the nerves that leave the brain that are in control of things like heart rate. The parasympathetic nervous system typically, if I can generalize, which is hard to do, typically slows things down or relaxes things. The sympathetic nervous system typically speeds things up, okay? So the nerves that leave the brain that actually go to the heart are from the vagus nerve, which is one of the larger parasympathetic output nerves of the autonomic nervous system. And these release acetylcholine, which slows heart rate, right? And they release acetylcholine to these pacemaker cells. The sympathetic nerve are called cardiac accelerator nerves. They release epinephrine. Actually, they release norepinephrine. You would put an N-O-R in front of that. And they would speed up heart rate. Nora means from the nerve, right? If you see epinephrine by itself, that's typically what we consider adrenaline. I really treat them very similarly because they do the same thing. They are going to increase sympathetic outputs to the body. But norepinephrine is released from the nerve. Epinephrine is released from the adrenal glands. Does that make sense? So one's released into the blood, epinephrine. One's released as a neurotransmitter, norepinephrine. They do vary, and I can't lie to you, they do vary slightly in their structure, but it's a very slight difference. So you can see here, here's normal kind of action potentials coming from pacemaker cells, and then here is what happens when you add a huge burst of acetylcholine. You flatline it, and then for a couple beats, and then it starts picking up again. If you add just a drop, it'll start to slow it down, right? Slow down heart rate. Here, we notice we have normal, and then you add some epinephrine, and then all of a sudden they get closer together, right? So with the parasympathetic nervous system, you flatten the funny current, With the sympathetic nervous system, you steepen, right, the funny current. Right? You reach threshold faster or slower, correct? So the question is, what is this funny current? Right? What is this, what they call pre-potential spontaneous depolarization? So I already told you that the potassium channels they're thought to be, at least some of them are thought to be slightly modified, right? They're gated, they close at a certain stimulus, which is -60, right? Which is really negative. So there are two other channels here that are going to respond to reaching resting membrane if the potential again and open in sequence. And so these channels have a name. They're called HCN channels. And those are actually the bottom of the slide, but I know you guys, most of you take notes. So they're called HCN channels. These are funny current channels. So I like calling them funny current channels because I just think it's funny that they named them funny current channels. So what this stands for, the H stands for hyperpolarization activating, right? Hyperpolarization activating. The C stands for cyclic because they open and close in a cycle. The N stands for nucleotide gated. Nucleotide gated. So you got hyperpolarization activating, cyclic, nucleotide gated channels. Now you know why they call them HCN channels, right? That's a mouthful. So what does the name mean? So cyclic, open, close, open, close, open, close. Hyperpolarizing, what opens them is a hyperpolarization. So this is what's cool about channels is all of them are set differently from one another if they're voltage gated channels on something we call threshold, right? These guys' threshold, these funny current threshold is negative, really negative charge. That's when they open or close, right? Because the potassium channels are closing, they're not open, right? So remember, a voltage gated channel doesn't always have to open, it can close, right? So the potassium leakage channels that are HCN channels are thought to be HCN channels, close when you hit -60, and they push it up a little bit, right? So that you start creeping positive. But there's not enough of them. You don't close like 50, 60, 80 of them. You only close a few of them. So not enough potassium's really leaking to really push me up any further than maybe a third of this line, okay? But once you get up to about -55, -50, then an HCN sodium channel opens, all right? A funny current or an HCN sodium channel opens. That's our first channel, and that pushes us a little closer to threshold. But we're not quite there. The last third to push us is a T-type calcium channel. All right, T-type calcium channel. So they call it T, I don't call it T. T means transient. So it opens at a middle, kind of a middle threshold, and it opens and closes really fast. Open, close. Okay, open and closes really quickly. And it pushes us, our final third, to right here. And when we hit threshold, we reverse our membrane potential. So where the video ended yesterday, and I'll pick it up right now, is I was talking about the autorhythmic cells, right? So we talked about funny current, right? So our funny current here is because of those HCN channels, those hyperpolarizing, activated nucleotide cyclic channels that include some potassium channels that close, some sodium channels that open and close, and then a T-type calcium channel that opens and closes, right? When we hit threshold after the T-type calcium channels open and close, then voltage-gated sodium channels all along the surface of our autorhythmic cells here, like in the SA node, open, and this L-type calcium channel opens and reverses our membrane potential. And so we got this upward swing that peaks when the calcium channels close, and then potassium channels open, voltage gated, that return us back to rest. And then we creep again, right? We never stay at rest. And that's the big thing about these autorhythmic cells is they continually depolarize. This L-type channel here is different than the L-type channel in the contractile cells. We called it isoform, an isoform. They have different isoforms. The isoform here has a slight variation in the amino acids that make up the protein and therefore have slightly different properties. And of course, got a nice animation up here that shows you kind of how this works. Okay, so that can lead us into our discussion and what we covered a little bit already on where these autorhythmic cells are found, right? So we have a couple nodes or groups of cells. They're called nodes. We have an SA node and an AV node, right? So the SA node is called the sinoatrial node. And it is the fastest of our depolarizing cells. That is, it spontaneously depolarizes faster than any of the other autorhythmic cells in the heart. And therefore, it's called the pacemaker. So when somebody gets an artificial pacemaker, what they're getting an artificial pacemaker for is the SA node's not working right. Or the SA node has been cut off from the AV node. All right, and that can happen. For example, in a heart attack, if you have a heart attack that destroys or kills certain cells, particularly those of the internodal pathway, then you can't communicate anymore with the AV node. And then the atria and the ventricles are contracting on sequence, and it makes the heart very inefficient. Then you can add a pacemaker to kind of overrun that. So these control the basic rhythm of the heart. And they depolarize anywhere between, 50 and 80 times. 60 is usually 60 to 80 or 90 times a minute to give you your basic rhythm to heart rate. The AV node, on the other hand, is going to be found in the connective tissue between the atria and the ventricles. And remember where the valves are that separate the atria and ventricles? That's all connective tissue that's electrically neutral. So action potentials that spread across the atrial network will not just automatically spread into the ventricles. So that's why we have to stimulate another node of cells, which are called the atrioventricular node, which is found in kind of the connective tissue between the atria and ventricles. We also have an internodal pathway that will connect the SA node to the AV node. And we can see that in a slide or two. I'll show you the kind of this autorhythmic network kind of separated out from the heart so that you can see how they all work together and how they're organized as far as their structure and location in the heart. So the AV node is a little bit slower. If it were to be separated from the heart, it would only depolarize somewhere around 40 to 50 times a minute. And that can help control heart rates. If it were left on its own, it could actually control heart rate fairly well. But it is slower than the SA node, and therefore the SA node will depolarize way before and spread to the AV node way before the AV node would actually fire. Right? So the SA node kind of controls and coordinates AV depolarization. The AV node is pretty interesting. It is not directly connected to any contractile cells. The SA node, on the other hand, is. The SA node spreads the action potential to the cardiac contractile cells around it via gap junctions. Okay? And so basically when these cells, I always say fire or depolarize, they release this big wave of positive charge, these action potentials, the calcium will spread into the contractile cells that make up the entire network of the atria and spread, like a wave, if you will, of positive charge that will spread from the SA node down towards the connective tissue septum that separates the atria from the ventricles. And when that positive charge hits the connective tissue, it dissipates because it can't pass to the ventricular network. But there are some specialized cells that are going to run from the SA node to the AV node, and they're called internodal cells. All right, internodal cells. And those internodal cells will deliver action potentials to the AV node. The AV node then is going to be connected to more of these specialized long conducting cells that are called Purkinje cells or Purkinje bundles. They're called branch bundles, and you can see the AV node is directly linked to those via gap junctions, and they act as wires or antennae that spread the action potential down through the interventricular septum. And notice they come down and then they bend on either side and then branch into individual Purkinje cells that deliver the action potential first to the apex or bottom of the heart and spread it upward. And this is very purposeful in the sense that if we were to start the action potential up here with the AV node, then the spread would be down and the contraction would be down, right? And the blood would be pushed down and then up. Remember, with the heart organization, the aorta and the pulmonary trunk, which are the two outlets of the heart, they're up here, right? Up by the atria. So we have to want to push blood up. So if we start the action potential down here and we start contraction down there and upward, it'll more effectively push blood into those blood vessels. It also allows for even distribution immediately to the large ventricular network because it's much more massive than the atrial wall. There are a lot more contractile cells. And so this allows you to instantaneously deliver action potentials at multiple spots that can then spread evenly through gap junctions of the ventricular mass. And that will allow for coordinated contraction. So basically this autonomic network is going to involve two nodes, an SA node, an AV node, and then a bunch of connecting wires or cells that are elongated that are specialized cardiomyocytes that, remember, that we call them Purkinje cells. They lack a lot of the organelles, and the myofibrils act in the myosin, and they simply conduct the electrical current. These cells also can fire on their own, but they're really slow, anywhere from 10 to 30 depolarizations per minute. And so they could not control heart rate effectively in a mammal like us. So if you were to lose your SA and AV nodes, say in a heart attack, then you would need a pacemaker, right? You would have to have a pacemaker. So this is a cool little picture that shows just an increased magnification of the SA node, our pacemaker. And you can see that it's going to fire regularly, right? Because of those funny current channels and the lack of rest that these cells have because of how the HCM channels behave. And they're going to send pulses of positive charge in the form of calcium into gap junctions that are directly connected to your contractile cells. And then you spread it evenly through all of the atrial network because of the intercalated discs and all the gap junctions that connect the atrial network together. You also notice that the action potential is slightly different with the contractile cells versus the autorhythmic cells. There's a plateau here, right? That is a calcium plateau. And I've talked about this a little bit, but it's because their L-type channel is an isoform that's slightly different. And when their L channels open, L-type calcium channels open, they stay open for 300 milliseconds before they close. Okay, this slide here shows you that autorhythmic network set up for you. So I found an image here from an anatomy textbook that kind of pulls it out off of the web that shows you the entire kind of autonomic, or these intrinsic, I should say, not autonomic, intrinsic pathway of stimulation that happens within the heart. Here's your sinoatrial node that would be up in the right atrium. And then down here is your atrioventricular node that would be between the atrium ventricles in that connective tissue layer that supports the valves. And these are the internodal pathways that connect the SA node to the AV node. Now, interestingly, the AV node doesn't fire immediately when it's depolarized. It's because the channels are slightly different in its membrane, and they kind of delay for a few milliseconds before they actually depolarize, and it's called the AV node delay. And what that allows is for the complete emptying of the atria before the ventricles are depolarized and contraction starts. The cool thing about this image is, and I really like this image here, is it shows the spread of the action potential, right? With each beat. So our beat starts up in the SA node, which depolarizes first, and then it's going to slowly spread towards the apex, right? So you can see it's going to spread downward. And as it spreads downward, and this is pretty fast through the gap junctions, then the atria start contracting. But notice it slams into that connective tissue layer that's inerts, if you will, to electrical potential and dissipates. But we, at the same time, those internodal pathways have stimulated the AV node, which now fires. But instead of spreading through the ventricular mass, it actually spreads down through the bundle branches and the Purkinje cells that connect the AV node to the ventricular mass down in the apex of the ventricles. And so you can see that it spreads down what we call the interventricular septum, and then it's going to spread upward from the apex up, and contraction will then happen from the apex up towards the valves and push blood into the aorta and the pulmonary trunk right here. And we'll go through blood flow in a little while when we talk about the heart. Now, you can measure these waves of the entire heart. And we'll look at these waves of depolarization. That's what we're going to do today in lab with the EKG, is measure the entire electrical output of the heart. All right, any questions on the autorhythmic cells? Now, once we spread our action potential to the contractile cells, whether that's directly through the SA node or indirectly through the Purkinje fibers, right? We are going to send positive charge through gap junctions into the cytoplasm of our contractile cells. And this is kind of a nice schematic from your text and the steps of depolarization and repolarization, right, in our contractile cell. And we're going to start up here, and you can see we can go 1 through 10 here. Number 1, it says action potential enters from adjacent cells. So this would be gap junctions, right? But what I want you to realize is that the surface of your cell, these are long cells, right? So the surface of your cell on one end is going to be stimulated by calcium flowing in. But we have to spread that action potential across, right? Only so much calcium can enter the cell at any one time in order to depolarize it. So we're going to have to open channels on the surface of our contractile cardiomyocyte. And the channels that are on the surface are sodium channels, mostly sodium channels. A few calcium channels, but they're mostly voltage-gated sodium channels, which is the one major difference with the contractile cells versus the autorhythmic cells, which only use sodium channels in funny current. Right? They use calcium channels only. These sodium channels are limited to the surface of the cardiomyocyte. When you get to a T-tubule and that depolarization goes down into the T-tubule to stimulate the deep parts of the cytoplasm, the T-tubules end really close to the sarcoplasmic reticulum, or the ER. Then you're going to have L-type calcium channels. There are very few to no voltage-gated sodium channels in the T-tubules of the contractile cardiomyocyte. Just L-type calcium channels, which are slightly different in isoform than the, as I mentioned already, than the autorhythmic cells. So when this channel opens, it stays open for a long period of time. Calcium is going to flow in and form what's called a calcium spark or calcium sparks. That is going to depolarize the area of the cytoplasm around the sarcoplasmic reticulum, which will open the calcium channels. They're voltage gated also. In the SR, which are called RYR channels or rhinodine channels. Right? These rhinodine channels are the same channels that are found in the ER of skeletal muscle. That's going to cause the cytoplasm to be flooded with calcium. because the ER can hold like 20 times the calcium concentration that the cytoplasm could. And so it can really sequester or concentrate calcium. So tons of it are going to enter this space and cause a calcium signal. So it goes from a spark to a wave or signal that spreads across the myofibrils. Right, where the SR sits over top of the myofibril section, like a big net of tubes, and that'll bathe the myofibrils in calcium. And what's covering up the myosin binding site on actin is troponin, right, which is the regulatory protein, and calcium will bind to that, which will change its shape, and it'll slide out of the way and allow actin and myosin to interact and cause contraction. Now, once the action potential is over with each beat, right, then we have to remove the calcium in order for the muscle to relax. And so after calcium stops flowing in and you have repolarization happening, right, because potassium channels open, then all these calcium channels close, and the SR is going to be pumping calcium back in. These pumps, these calcium uniporter pumps, they expend ATP, and they're working all the time. And they are overrun initially by the opening of the RYR channels or the ryanodine channels. But once they close, then they can start doing their job and returning most of the calcium back to the SR. There's also a calcium exchanger up here in the cell membrane, which is called the sarcolemma in muscle. That is a sodium-calcium exchanger called an NCX exchanger. That's a special exchanger or antiporter that uses a sodium concentration. Sodium flows down its concentration gradient to pump calcium out to the extracellular space, and that will be run by the sodium-potassium pump, right? And what's interesting, and I think I mentioned this towards the end last time, is there are a couple drugs, once we understand this mechanism, that target this sodium-potassium pump, which each kind of type of tissue has its own isoform of a sodium-potassium pump. And there is a plant that's called foxglove, and it's a European plant. And it produces a toxin, actually. It's really a pesticide. It prevents insects from eating it. That is called digitalis. That's the name they've given to it. The actual plant's name is Digitalis lateralis, is the actual scientific name. Or it's called Dixoxin, is the drug name. And this drug, what it does is it binds to just the isoform of the sodium-potassium pumps that are found in contractile cardiomyocytes. And it slows the pump. So this pump is less effective. You're not pumping so much sodium out and bringing so much potassium in, which is going to slow this exchanger, isn't it? Or limit how much calcium the exchanger can pump out. In that case, calcium is going to remain in the cytoplasm, isn't it? Where it shouldn't be. Not enough to cause hard contraction, but enough to allow the next wave of depolarization to force a stronger contraction. The more calcium you leave in a muscle cell, the harder the contraction, right? Because the more actin and myosin you can recruit. So actin and myosin recruitment is based on calcium concentration. So this is a wonderful example of a naturally produced toxin, pesticide, that medicine has figured out can work in the body to treat disease. And this is one of the older medications that are used. It's used for congestive heart failure. When the heart stops beating as hard as it is because of damage or age, you can use digitalis. They can give it to patients in order to cause harder contraction. My wife's a pharmacist, so I asked her last night, I'm like, do they still use digitalis because it's an older drug? And she's like, yeah, it's still a first-line defense for a lot of patients that are first diagnosed with congestive heart failure. So what's cool about these mechanisms is once you understand them, then you can start, customizing treatments for disease states if you can target certain proteins. Pretty cool, right? Okay, so that one, we talk about an EKG really quickly, right? Then I'll let you guys work in the lab. So that's what an EKG wave looks like. It looks a lot different than either, right? The action potential of a single autorhythmic cell or a single contractile cell. And that's because when we measure those, we actually, what we do is we produce what's called a microelectrode, right? And so we'll, find a cell and we'll produce a electrode that we actually stick into the cell, so into the individual cell, right? And that'll be attached to like what we call an oscilloscope, and will allow you to measure the millivolts, right? So how do you make one of these? Have you guys seen those glass micropipettes that you use with the little bulbs that you suck up solution with? They will make a stretcher, and it's an art. You actually have to do it a lot in order to be good at it. But what you do is you warm up that thing under a flame, and then you stretch it, and it'll stretch the glass out to a fine point, and then you break it off, and it'll be a micro point that you can then use a extender and extend it into a muscle, and then you can puncture cells with it. Then you fill that glass micropipette with potassium chloride, right? Electrolyte that you can then pick up electrical activity. So that's how they make those. So I used to actually teach a lab where we would do that with frog muscle, but I can't make the pros. I mean, I don't first have the machine to do it, and I sucked at it. So now back in grad school and at Wittenberg, we actually had a neurophysiologist, so he would make them for me. But so I don't do that anymore, but that's kind of how you make them. Now, the reason this looks so different is because this is now we're going to put those little patches, you see it right there on the table, we're going to put those on the surface of your body. And now you're going to measure electrical output of the entire heart, right? It picks it up. It's picking up this electricity that's produced before each beat. And so now you're getting all of the electrical activity of the hundreds of thousands, the millions of cardiomyocytes, right? And obviously, you can see there are three major waves, right? Now, I will tell you there are other waves. You just don't always see them, or you need a much more sensitive EKG machine to do it, which are tens of thousands of dollars, right? The ones they use in hospitals, for example. So we're going to use what's called Eventhon's triangle, which is basically three electrodes, right? We're going to use a positive and a negative end, an anode and a cathode, and then we're going to have a ground, right, which typically goes on your ankle. And so we'll put one on the ankle, I think, and one on each wrist. And then you sit still, and the sensitivity of our transducer there is pretty good, so we'll be able to pick up your electrical activity of your heart. So the one thing an EKG is, or they say ECG, right, is just a measure of the electrical activity of your heart. It doesn't tell you anything about how your heart is performing mechanically, all right? But it does tell you or give you some assumptions, or you can start assuming what's wrong mechanically. So if you were to go into the hospital, like I did, and when I passed out, they're obviously thinking something's wrong with your heart. They put you up. The first thing they can do is do an EKG really fast. You're going to see it's really easy to put the electrodes on and say, oh, there you go. And mine doesn't look right. So what did they do? They admitted me and then tried to figure out what's going on with other tests, right? They did an echocardiogram, so they looked at then how the heart's performing. And the electrical activity does give you some information about performance, but you have to you have to basically support that with some other tests. If that makes sense. So these waves, these three waves that you see, the waves are blips, right? So you're going to have a baseline, right? And then you're going to have what are called waves and segments. So the segments are the flats, plateau areas. So those are called segments. And then if you have a blip in the positive or negative direction, it's called a wave. Now, usually what they do is they run it in a certain direction so that your waves look positive. But you're going to see this today. You flip the electrodes and you can make them negative. Now, if you flip them positive and you get a big negative blip, then that's bad. I mean, there's something going on. And you'll see that with mine. All of a sudden, mine will be normal, then it'll be a big negative blip when I pull it up. Or it'll just flatline. You won't see anything. So it's the electrical activity didn't fire right with each beat. So this first wave here is called the P wave. All right, the P wave is going to typically be a little bit smaller than the one on the third wave here. The P wave represents atrial depolarization. All right, it represents atrial depolarization. So right over towards the end of the P wave is when the atria actually start contracting. Okay, and then you got a small segment, right, as the electrical activity slams into that connective tissue layer. Then it travels to the AV node. The AV node fires, and then you get a negative blip traveling down. That's because the depolarization is traveling down the interventricular septum, right? So it travels down, and then all of a sudden you start the big depolarization of the entire ventricular mass. And so obviously it's much bigger, right? And then all those calcium channels close, and you repolarize, and then you get another segment. This is called the QRS wave. All right, it's a complex wave because of the Purkinje cells and how the AV node is connected to the ventricular mass. The QRS wave represents the ventricular depolarization. Then you get a segment, and you get another blip that's more rounded here, and this is called the T wave. The T wave represents ventricular repolarization, right, where you're bringing the contractile cells back to resting membrane potential. Now, there is an atrial repolarization wave. It happens in the middle of the QRS wave, so you don't see it. It's covered up by the QRS. Now, these segments, you can see there's a PR segment. So from the end of the P wave to the beginning of the R wave, there's a ST segment, QRS to the beginning of the T wave, right? There's even a small blip that you sometimes see right after the T wave that's called the U wave. But I never talked about that. They don't use it often diagnostically because sometimes it's there and sometimes it isn't. So what do they use this for? The first thing you do is get heart rate on it, right? And if a clinician takes an EKG, what they're going to look for are the three waves. You see the three waves. That they look like they're pretty uniform from one beat to the next, because each one of these represents a complete heartbeat, right? A cycle through the electrical wave causes contraction and relaxation. Some things you could see. There are certain heights and widths to these that a clinician learns that are what we consider normal. So you can imagine they've taken millions of these across the United States, and they have what is considered normal, right? Normal heights and widths to waves, normal lengths to segments. If you have increased or decreased segments, it typically represents a pathology. I'll give you an example. If the T wave is flat, then that means your oxygen, typically the oxygenation to the ventricular mass is being hindered, or you have cardiovascular blockage, right? You have coronary artery disease. And if it's really flat and you're having chest pain, oh boy, right? It's a good indication that, hey, you need to get in and look at what's going on with blood flow, right? Sometimes if the QRS disappears and you get a P wave, nothing, a P wave, and then a QRS wave, and a P wave, and a P wave, and a QRS wave, that means that you have what's called a third degree block, which is the intranodal pathways have been disrupted, right? Because remember, the SA node fires faster than the AB node, and if you've separated them, now the SA is firing, then the AB fires. So you'll get several P waves, right? And then a QRS. So that's another example. And then you'll see mine and be like, oh my Lord, right? And then it's a mess. But so there are people that can read these really well. Can I read an EKG really well? No, I'm not a clinician, right? So we're not going to read yours, and I'm not going to be like, oh my gosh, there's something wrong with yours. We'll just look at them; they'll be normal. But somebody that does these can actually read them for long periods of time. If they want to see how your heart's performing over a long period of time, they now can give you an EKG unit that you carry around with you, right? So, for example, before I got my ablation, my cardiac surgery, I had to wear an EKG unit for like 23 days, and it was. I mean, they're glued to you, so they itch, and you had to cover them up, and you can only shower so often. It was pretty painful. And I like to work out, and I sweat like a maniac, and then my things started peeling off, so I had to tape them down. But anyway, it simply just measured my heart EKGs 24 hours a day for over 20 days, over 2 weeks, and then they can build a kind of data set on it. And what was really interesting with my heart before my surgery. My heart was skipping beats 45% of the time. That's incredible. My heart was performing like that of a 75-year-old, and I'm 50. So and that's why I felt so bad a lot. And so they went in and fixed it, right? Like that's what I talked about. So